Hello, everybody. So just want to say thank you to the organizers for inviting me here to Kiev. It's my second time here. I think I was here 3 or 4 years ago for XP Day, so it's great to be back. The weather's a bit better than it was back then. Last time I came was in December, and I didn't bring enough clothes. Now I'm overdressed. But thanks so much for coming along. This talk's going to be on application security and microservices. I'm hoping a large amount of this talk will be quite generic to any kind of development. I'm going to definitely talk about some specific issues associated with microservices, but a lot of this is going to be generic advice as well. So even if you're not using microservice architectures, there should still be some good practical advice in here. Contrary to the app, I don't work for ThoughtWorks. I haven't worked for ThoughtWorks for a couple of years. I now actually run my own company called Sam Newman and Associates. I'm available for training and all those sorts of things and workshops. But without talking too much about me, I want to actually ask some things about you. How many people here are a doctor? If you can put your hands up if you're a doctor. Right, now, I mean a medical doctor, like a proper doctor. Anyone here who's a proper doctor? Anybody here a registered nurse? No, a healthcare professional. Are there any healthcare professionals in the room? I can't quite see. It would be concerning if lots of hands went up, because then I'd think I was in the wrong conference. All right, OK, so I'll ask a different question. How many of you know that it's important to wash your hands after you've been to the toilet? Right, OK. I'm going to just ask why everybody's hand isn't up. I mean, I did ask a very specific question, which is how many of you know how important it is to wash your hands, not how many of you actually wash your hands after you've been to the toilet. Those are two separate questions. But nonetheless, the reason I ask this is because you're not medical professionals. You're not trained nurses or doctors. There's no epidemiologists in the room. Maybe a couple of you have played Pandemic, the board game. Maybe that's about as far as we go. But that you all understand the importance of washing your hands after you've been to the bathroom, because you understand that that's one of the things you can do to stop spreading diseases. You don't have an in-depth understanding of viruses and bacteria and how infections happen, but you know this is a good common sense advice. And the reason I raise this is I feel that when it comes to security, we're sort of in a world where we may have been 15 years ago with testing, where what we used to do with testing is we'd go, oh, well, testing is a very specialist topic. It's very advanced doing testing. And I'm only a developer with a tiny brain. I couldn't possibly test my own code. So I'll have somebody else do that for me because it's a specialist skill. You absolutely have to be a specialist. And we got better at that. I mean, how many people here write tests for the code they write? You put your hands up, right? That's most of the audience, and the rest of you should be ashamed of yourselves. But that's fine. But with security still, we go, no, that's OK, because security is very, very hard. And I couldn't understand it with my tiny developer brain. And so I'll have a specialist do all the security for me. And what they'll do is they'll sprinkle security onto my application later on. I'll do it all now. And at the end, we'll just sprinkle in all that lovely security at the end, just like we used to sprinkle in the quality of our apps. Now, I absolutely think there is a role for specialist security people. It's a very deep field. It's a very complicated field. But just like with doctors or nurses, where you need specialists, you need specialist healthcare professionals, you need specialist security professionals, there are still things that we can do as developers around security that are kind of the same thing as we do when we wash our hands. Basic hygiene. I think the reality is at the moment, though, that there's not a good awareness about what that basic hygiene is, and nor do we always think it's our responsibility. We just assume it's going to be for somebody else. So I'm going to give you just some very simple things to think about today that I think all of you can make use of in your day-to-day work. So that's the positive side. The negative side is, of course, I have to scare you because this is a talk about security. So how many people here have seen this website before? This is norsemap.com. Has anyone been here before? A couple of you, right. So this is a company that, amongst other things, monitors what's happening out there on the public internet and actually create this lovely thing called the attack map. And it shows sort of the live or semi-live attacks that are going on the public internet. So I screen capped this a while ago, so hopefully it will start playing in a moment. And so what you're seeing here are various different attacks being made from different parts of the world over the public internet. It's all quite interesting. You see somebody's very annoyed at somebody on the west coast of America at the moment, and in a minute someone's going to get very annoyed with somebody in the Middle East. And there we go. Yes, someone's very annoyed with somebody in the Middle East. Now, this is just the background noise of the internet. These are just various denial of service attacks that are happening. These are things like ping overflow attacks. You can actually see down here the different attack types and see that some of them are quite basic, what's happening here. This is the reality of what's happening on the internet. The question isn't if your site is going to be attacked by something. The question is when. If you have a website on the public internet, something is going to decide to have a go at you. And it may not be directed at you personally. You just may be collateral damage in somebody else's attack. So this is the background we're operating in. This is the background we're operating in, that things are just happening. There are botnets running out there that are just thinking, oh, okay, I'm going to look for machines with vulnerabilities. Now we think about the world of microservices. This is how I draw microservices. I always draw them as hexagons. If you've seen any of my talks before, this won't be unfamiliar to you. And when we talk about microservices, the definition that I use when I talk about microservices is this: independently deployable services that work together, modeled around a business domain. I don't talk overly about technology that much in terms of what a microservice is. Technology is a means to an end. The key thing here is that what we're looking for from our microservice architectures are things which are independently deployable. I should be able to make a change to a service and deploy that service into production without changing anything else. Now, microservice architectures are quite interesting because they give us a whole load of options. They give us a whole load of opportunities to do things a bit differently than we may do with a monolithically deployed application. With a monolithically deployed application, where maybe we've got all of our data in one database, all of our processing is running in a single process, we sort of have this challenge around security in terms of vulnerability. We quite literally have all of our eggs in one basket. If our database gets hacked, they get all of our data. If our process is compromised, they get all of our processes. With a microservice architecture, we have this nice concept of isolation. These things are independently deployable. These are separate services that own their own data. Therefore, potentially, we have the ability to practice defense in depth when it comes to protecting our applications. We don't have one perimeter at which to defend ourselves. We have multiple perimeters at which to defend ourselves. We can run our processes, we can run our microservices on different subnets and different VPCs, if we're on Amazon, for example. We can set up network-based routing to make it harder to gain access to some services from some other services. We can encrypt at rest more easily. And this is great. This gives us a fantastic opportunity to protect ourselves. This concept of defense in depth comes up time and time again in security engineering. The idea that one prevention mechanism isn't necessarily enough. You need lots. And that's fantastic. Separate processes give us many, many more options to protect our application. And so from that point of view, microservices are definitely a benefit. The problem is that microservices give and they take away. And one of the areas they also take away is that they also drastically increase our surface area of attack. All of that information that used to flow within a process is now flowing between processes across networks, opening up the possibility for a malicious party that gains access to your network just to sniff the traffic. It's surprising how many of the clients I have where they're just running their microservice systems just over their public networks with no encryption or anything else. Anyone on that public network can just go and sniff the traffic and see what's going on. It's even more interesting how few of them actually have protection at the endpoints themselves. People are worried about people gaining access to your database and hacking your database. But if I'm on your network and you've created a lovely REST API for your customer service with a nice Swagger documentation, oh, look, I can browse around and find out how to make the requests I need to make. And now I can run nice little REST requests using curl and extract all of your user data in JSON format. You've nicely formatted it for me and everything. Isn't that kind of you? So this is the downside. We've increased our surface area of attack. And when it comes to security, time and again, we see this sort of give and take, give and take. Now, I actually think that if you are sensible about security, a microservice architecture has the possibility of being significantly more secure than a similar monolithic application that's sort of solving the same purpose. But if you go into it without thinking about this stuff, you'll probably end up with an application which is less secure than a monolithic counterpart. And so you do need to go into it with your eyes open. Now, as developers, I think we often fixate a bit too much on stopping the bad thing from happening. But when it comes to application security, we've got to think a bit more broadly than that. There's a sort of a four-part model we used to use at ThoughtWorks, which I find very useful when thinking about the landscape of what application security is and where I should be spending my time and energy. So yes, we absolutely need to focus on prevention, preventing a malicious party gaining access to our data, gaining access to our process. But we also can't only spend all of our time here. We've also got to think about what do we know if someone's gained access. So we stop something bad from happening, but do we even know that it's happened? Because a lot of people don't. A lot of people have this sort of hive mentality. We stop you at the gate, but once you're inside, we assume, oh, well, if you're inside, it must be fine. We're not going to worry about it. So you actually need to detect if something bad has happened. Once we've done that, we need to know how to respond. This is mostly soft skill stuff. This is not really about technology. This is mostly about knowing what to say and when and from whom. This is actually largely about having empathy for your users. The nice thing is, in this particular field, there are so many bad examples of organizations responding to security incidents that this is quite an easy section to talk about. And finally, when all that is said and done, we've got to recover. So I'm going to talk to you today about all four parts of this model. How we stop bad things from happening, how we detect if they have happened, how we respond, and how we recover, and looking at that in the context of a microservice architecture. We should start off, though, by looking at how we prevent malicious parties from gaining access. And I want to tell you a story about a client I worked at a few years ago. This was just post the Snowden revelations about the NSA. And so lots of organizations started becoming a little bit more aware of how they looked after data in their organizations. And this particular client had decided to create a brand new InfoSec team that were going to address security concerns in that organization. And so they started looking at all the different ways in which people could gain access to the information this organization held. And one of the things they were quite concerned about was premise security, so gaining access to an office. And they did a bit of a survey of the offices where I was based at the time in Australia, and they were doing a survey of the offices around there. And they came back with a proposal that we should install CCTV cameras in the foyers of the office. The idea was that it would sort of deter people from coming in, gaining access to the building, because one of the issues in this particular organization was once you had access to the physical premise and you plugged in an Ethernet cable, you had access to the whole public network inside that organization. So they thought, well, we'll put a CCTV camera up in the foyer, and that will stop people or deter people from coming in. It would also help that if something does happen, we've got a chance of finding out who did it. And so they sent round this note saying this is what we're thinking of doing. And this caused a big uproar in the organization, lots of people being very paranoid and also raising privacy concerns, saying, this is my, what are you doing? Do you not trust me? This is me, don't you trust me? What are you spying on me for? And this went on for a long time. And it got a bit nasty, actually. All these developers going, "Arr!" And the InfoSec people go, "Ooh!" And that went on for about 2 weeks. And then eventually, one of the people, it was in the Melbourne office, said, before we spend thousands of dollars installing a CCTV camera, should we make sure the front door lock actually works? Because it turned out for a good couple of years, the front lock to the Melbourne office was notoriously bad, and frequently you'd leave the office, think it was locked, and only to come back in the morning to find that the door had just blown open because the door didn't properly latch. And they said if our goal is to stop someone gaining access to our building, maybe spending $100 on a locksmith to fix the door lock is a lot more sensible use of our time than installing an IP-based CCTV camera for thousands of dollars. And they were right. And this is the actual issue when it comes to prevention, is that as developers, we often are focused on the shiny thing. We see one potential vulnerability and we fixate on that without actually stepping back and looking more holistically at the ways in which people might gain access to our system. There are other ways in which people might gain access, and have we thought rationally about the other things we should be doing? There's a technique you can use to create a framework for how you think about this sort of stuff, and that's it's a concept of threat modeling. There are lots of very good threat modeling techniques out there. Stride and Dread from Microsoft are both worth looking at. There's one sort of subpart of that which I want to share with you to give you an idea of what's possible, and that's this concept of attack trees by Bruce Schneier. So with an attack tree, what you do is you basically look at some goal that a malicious party is trying to achieve, and you enumerate the ways in which they may gain access to that particular sort of goal. So in this situation that Bruce outlines in his paper, he talks about the goal of an attacker trying to open your safe. So if I want to open the safe, what are the ways in which I could open the safe? And you just enumerate those. So I can pick the lock, I can learn the combination, or I can cut the safe open. And you keep going. Okay, well, how could I learn the combination? Well, I could find that combination written down. I could get the combination from the target. At this point, it starts feeling a bit like a Jason Bourne film, right? There's people running around trying to kidnap people. How could I get the combination from the target? Well, I could blackmail them, I could threaten them, or I could bribe them. It's very interesting. A large amount of sort of application security does come down to people factors. Once you've done this, then what you do is you look at the different mechanisms that the attacker could use, and you decide, you give it a weight. Like, how difficult is that avenue to use? So, and typically here we're talking in terms of money, or something like money. Often the goal of security engineering isn't to make something impossible, it's actually just to raise the cost of a certain type of attack so high that it's no longer financially viable for an attacker to use that attack mechanism. This is why we use long encryption keys. Theoretically, an attacker could break that encryption key, but they'd have to spin up so many machines that it would take a very, very long period of time and also cost them way more money than any benefit they're going to gain. So in this particular situation, we might think, well, it's highly unlikely they're going to be able to pick the lock. We've bought the best lock you can buy. We've done all the research. We're pretty confident that there's no easy way for them to get that lock open. On the other hand, we think it's quite likely that they could find the combination written down, because I can see George's desk from here, and George has the combination on a Post-it note on his monitor. Now, lots of passwords end up on monitors. And so using this technique, you can actually start focusing your attention on the weak spots and saying, okay, these are the areas where we need to focus our attention. Doing some kind of threat modeling exercise is incredibly valuable because it ensures you're spending your time and effort in the right place, rather than being busy for busy's sake. You can do this stuff yourself. Do take a look at the stuff from Microsoft's Secure Development Lifecycle. It's really good stuff, applicable to lots of different languages. This is an area where maybe getting an external party in to help could be good. But just doing some basic threat modeling can help. But let's imagine that we've done this, and now we're bringing ourselves to start looking at a microservice architecture and to start thinking about how we might protect a microservice architecture. When we're looking specifically at microservices, the first thing that comes to mind is really the conversation about transport security. As I talked about at the beginning, with a microservice architecture, we've drastically increased the surface area of attack. The information that used to flow within a process now flows between services. So we've got to think about this. What are our options in terms of protecting that data as it flows through our system? Well, let's look at some options, and let's look at something. And a lot of people use HTTP as a protocol for communication between services. So let's start there. What could we do in the area of HTTP to protect ourselves? Well, we could start off with something like this, just using HTTPS everywhere. So all of our services, by default, are using SSL. Now, historically, when I was doing web development, like 20 years ago, I'm older than I look. We would never do this because it was slow. That was the argument given. It's slow. Or 25% of every request is taken up doing HTTPS. Turns out it's not true anymore because guess what? Apparently, there's this thing where machines get faster. So, that's less of an issue. The other argument was it's really painful, which is also just not the case anymore. How many people here have heard of Let's Encrypt? Okay. So some of you. The rest of you should take a look. So the Let's Encrypt is it's basically a foundation designed to help protect the public internet and raise the general level of security in the public internet. And one of the ways they're doing this is by offering a free certificate authority. So you can just go there and get a certificate to be able to run your website over HTTPS. And this is really interesting because when this first came out, people fixated on that word free. Oh, it's free. Oh, it's free. Oh, that's amazing. It's free. Free was not the reason you weren't doing HTTPS in the past. Free is like what? really, the blocker for you in enabling HTTPS on your website was going to Thwaite and paying $25 for a certificate for a year. That was the blocker? No, it wasn't that. It was the automation, because the process of issuing and renewing and installing certificates was all manual and painful. And that's the thing that Let's Encrypt people have sorted by developing this open source Acme protocol, which allows you to just automatically create certificates and install them and renew those certificates as well. This means those certificates actually can be quite short-lived, which in turn is a good thing, because you always want to have short-lived credentials if you can, as you can read up on how to do it. There's like one-liners to install on things like Apache and Nginx. And there are loads of other options. I mean, all the cloud platforms now provide the ability to issue HTTPS, even for use inside your perimeter. But we should understand what this gives us. So say I turn this on, and all of my services now run over HTTPS. OK, great. But what have I actually got out of that? All I've really got is the concept of trust in the server itself. The service I'm talking to, I can confirm, assuming I've done the right thing with my certificates, the service I'm talking to really is the service I'm talking to. So all this has really done at that point has stopped somebody else potentially masquerading as the service, which is a pretty advanced attack anyway. It also gives me some protection in terms of data at transit, protecting me from things like man-in-the-middle attacks. But chiefly, it does nothing about actually validating who the client is. So even if your service is running over HTTPS, a malicious party on your network can still freely run curl against your endpoint and extract the data they want. So, OK, it's a bit better, and it's actually quite easy, so maybe it's something you should just do anyway. But we're not all the way there. So now we need to start thinking about what we can do on the client side. How can I make sure that only authorized services can talk to my service? The other obvious option here is to look at something like client-side certificates, things like X509 certs and the like. Now, if we complained about server-side certificates, oh boy, are client-side certificates even more painful. And unfortunately here, the story still isn't great. I was quite hopeful a couple of years ago that things like Netflix's Lima PKI infrastructure was going to make this easier. This is a system that Netflix use internally for managing and issuing client-side certificates so that services can be authenticated when they talk to other services. Unfortunately, I haven't really seen it catch on, and it doesn't seem to be going anywhere at the moment. I'm hopeful that service meshes might solve these problems, by the way, in the future. I'll be talking a bit more about service meshes in my keynote tomorrow. So that's not great, but client-side certificates are quite useful because they do give the server or the producer some sense of trust in the consumer. So when a service is calling me, I can use the use of their client-side certificate, their client-side certificate to say, yes, that is the service I think it is. And so even if you have to install and manage these things manually, they might have a part to play. For example, here, where I'm going outside of my perimeter, potentially talking to an important third-party vendor over the public internet, I might decide to install a client-side certificate on an edge device, so maybe I'm not having to handle it inside my service stack. So giving myself some additional level of protection. There are other kinds of client-side authentication mechanisms. You can use things like API keys and HMAC. That sort of implies that the clients have a secret that they have access to, so a private API key, that they can then use to hash their requests and things like that. So HMAC is a really interesting thing worth looking at in this space. The big issue is still, how do you get the private keys to the clients in the first place? So you still sort of have that bootstrapping problem. Things like Vault can really help, so definitely take a look at Vault from HashiCorp. Now, at this point, we've really been talking about sort of stopping people looking at our data, masquerading as services, and client-side authentication in terms of services talking to other services. We haven't really, though, talked about the other problem that gets raised a lot, and that's a conversation about auth, specifically authorization and authentication of human beings. Now, the authentication of human beings in these kinds of architectures is pretty straightforward, so I'm not really going to dwell overly on that. I'm more going to talk about the authorization problem. So in this situation here, if I'm using, say, a mobile application or a web browser, and I come to that client, I probably have some kind of perimeter device that says, oh, you're not logged in, I'm going to redirect you. Maybe this is a traditional OAuth flow. and I'm going to get you logged in. OK, great. You're now logged in as a token that represents your logged in state. I then go to a web page and say, I want to see my account details. And to the music web shop, which serves up my website, I go to the page that says account details, and the music web shop goes, oh, you want your account details? Great. Well, to get your account details, I'm going to go and need to ask this service downstream called the user service, and that's going to get all the information that I need in order to render this page for you. This then opens up some really interesting challenges around how we think about the concept of authorization, especially when we're thinking about services that call services that call services. So the scenario goes like this. We start off, and I come along, and here I am as Bob. Bob's always up to no good in these security scenarios. So Bob is attempting to access a site, and it says, OK, you need to go and log in. And it says, yes, you are now logged in. So it redirects me around a login flow. So fantastic. So now I am logged in as Bob, and everybody's happy. So then I say, well, I want to see my user details. And the music web shop says, well, I don't actually have your user details, but I know somebody who does. So I'm going to go ask them. So the music web shop goes to the user service and says, I want Bob's details. Now, at this level, we might have service-to-service authentication going on. In other words, the user service can say, oh, you really are the music web shop. I know you're the music web shop. Great. And at this level, what most people then do is have this idea of implicit trust, which is to say that if I know it's the music web shop talking to me, I just assume by default that anything I'm asked to do are things that I should be doing. This is where most people get to. So in this situation, Bob says, can I have my details? The music web shop passes that request downstream to the user service, says, look, I need Bob's details. He's after them. OK, great, OK. So the user service responds by saying, here's Bob's details, and that renders the web page. And actually, this flow is completely valid. I've had access to information that I should have access to. Now we look at the more insidious problem. Here I am, I'm logged in as Bob, and I go to the music web shop and say, can I see Alice's details? Now, here's the thing. The music web shop doesn't hold any of that information. So why should it be making judgment calls about what I can or cannot do with a downstream service? So it just assumes, OK, well, I'll go ask. So it goes down to the music web shop and say, look, can I have Alice's details? And again, the user service goes, well, you're my good friend, the music web shop. And my good friend, the music web shop, you wouldn't ask me to do anything wrong, would you? Of course you wouldn't. So yes, of course, here is Alice's details, and then that information gets passed back up. This is an example of the confused deputy problem. It's a classic problem in security engineering. It's a situation where basically you trick an intermediate party into asking for information that you shouldn't be able to ask for. And this happens a lot in a microservice environment, because we've got to think about who makes the decision about what you're authorized to do. In this world, I could have the music web shop do authorization for all downstream requests. But how would that work? The music web shop would then need to know all the operations that could be called on all downstream services, and then know how to enforce those. And that's a lot of responsibility for the music web shop to have, and there may be multiple routes into that sort of system. Really, when we're thinking about how we think about microservices, it makes more sense for the user service to decide what I can and cannot have access to. And so what we want to be able to do is give the user service as much information as possible about the person making the request in order to allow the user service to make the right judgment call about what I can see. A really common way of handling this is to use something like a token, like a JWT token. So the JWT token, you take a JSON structure, and it's a similar algorithm to, a similar mechanism to HMAC. You basically use a key to encode a header of some JSON structure. So you might get a hash that looks like this. And this becomes a token that you could put into, say, your OAuth token, and that information gets passed downstream. So when I log in, this information about who I am gets put into this token. And when the music web shop makes a request to fetch Alice's information, it passes that token downstream. The user service has access to that token. It can validate that the token is real based on that hash without requiring a round trip. And it looks at it and says, well, you're asking for Alice's details, but you're Bob. And the rules in my service state that you can only ask for information that's yours unless you're in an administrator group. And so this allows you to push the decision-making around authorization to the services that are best able to handle those situations. Data at rest gets interesting. Data at rest actually is a lot easier in a microservice architecture because we actually can focus our attention on those areas that need it. We think about a large monolithic database. We often get worried about encryption because there's often an overhead of encrypting and decrypting our data in a database. The thing we're worried about here is someone gaining access to that data at rest and just stealing all of our data. There's always a question, so often people will start encrypting part of their databases. Maybe I'm just going to encrypt these tables because that's where my PII, my personally identifiable information lives. So I'm just going to encrypt that stuff. And then people miss those tables, and then bits of it get encrypted and bits of it don't. It all becomes a bit of a management overhead. But here, of course, I've got 4 different services. I can just look at those and say, well, where is the data that I'm most worried about stored at rest? It's the user service. Well, let's just encrypt all of it, just to simplify the whole problem. This becomes a bit easier. When it comes to prevention, though, there is one thing that you can do that's more important than any other. That is patch your stuff. So, another question for all of you. Can you put your hands up if you know that all of your machines are updated to the latest patch level at least once a month? We've got like 5 hands up in this room. So, that's a bit worrying, but not surprising. So most of the major operating system vendors, all the ones that I used, will roll out patches once a week. And yet, people in this room aren't even sure that they're updating them once a month. There was a study done last year that found that 44% of all security breaches were caused where vulnerabilities had already been detected but had not yet been closed. A lot of that were things that were not patched. So a large portion of security breaches are caused by unpatched code. And this is the problem we've got, is that we've got patching to think about at multiple levels. How many people here run on containers, for example? Put your hands up if you use container workloads. So probably about maybe a quarter of the room at most, but that's still sizable. So then you've got an interesting problem with containers because you've got to worry about patching at 3 different levels. You've got to worry about patching at the operating system, your host operating system, when your Docker engine or kube is running. So you've got to patch there. You've then got to worry about patching the operating system running inside your container, which most people forget about, by the way. And then you've also got to think about patching your application code running on that container. So a really interesting problem with containers is what we do is it's quite a nice thing, which is we create an image that represents our running, that's our service that we want to deploy, but that comes with that container image is the operating system that's going to run on that container as well. It might be small, might be like Alpine or something, but it's still there. We then deploy it and run it. And the only time that gets changed is if we roll out a brand new version. That means if you don't change that container image for, say, 2 weeks, 2 months, 6 months, it's running there with software that hasn't been patched for 6 months. So even if you're patching your host operating systems, you may well have running containers that have vulnerabilities in them. Now, technology is getting better to help us detect vulnerabilities in those containers. There's lots of people doing interesting things, like the team at Aqua, some of the stuff coming out from CoreOS. But it's still a big gaping vulnerability, especially in Dockerized workloads, where we use these things as being immutable deployments, but we don't really do anything with them once they're deployed in terms of patching, basic hygiene stuff. Things are a little bit better with application code. There's some really lovely tool chains out there that will look at the dependencies that you have for your application code and will tell you when new versions are available. Snyk is one service that I really like. It's a really cheap service. What they do is they look at, say, your gem files or your Maven dependencies and say, okay, well, these libraries are out of date, and what I'm going to do is I've spotted a new version where this critical vulnerability has been patched, and they'll send you a pull request. They'll automatically send you a pull request to update all the versions. You click a button, and it updates it all for you. Fantastic service, really cheap, very little excuse for not using these sorts of things nowadays. We should move on now to talk about detection, which is knowing if a bad thing has happened. How many people here have heard of shell shock? Very famous, 2 people, that's disturbing. Big outage that happened several years ago. Not big outage, big potential breach, where a vulnerability was found in Bash. And it was found that basically for 2 years, Bash had a vulnerability in it which potentially allowed an external party to gain access to your machine. Really big problem, because although we just detected it and we put patches out, we knew there was a 2-year window where we may have been vulnerable. And so inside ThoughtWorks at the time where I was still working, I sat down with the head of InfoSec and we said, well, how are we going to know if we've actually been hit by this defect or hit by this vulnerability? And the very first thing he said was, well, actually, looking at our application logs is probably the best thing to do because we can see traces of these sorts of attacks being used. But we found, actually, that our log retention policy wasn't really appropriate for this. We were storing logs for, like, I think it was 6 months at most in terms of just for sort of helping developer support activities. We weren't actually storing them for a long enough period of time. And so we actually changed our log retention policies in the organization around that, putting it out to 5 years. So log aggregation can really help. You get the logs into somewhere central. You can look and spot those sorts of traces. This is really is sort of low-hanging fruit. Some security appliances can help. Things like mod security, for example, will not only stop some sort of attacks, but will also detect things that look suspicious and could alert you to those sorts of things happening. And typically, you'd be deploying those sorts of things in some sort of perimeter. And of course, with something like microservices, you have the potential for multiple different perimeters. When it does come to detection of defects, a lot of it is about knowing if a defect exists in the first place, if there's a critical vulnerability out there. And a lot of people who adopt microservice architectures will also adopt this idea of polyglot, having lots of different programming languages. The issue, of course, is if you've got lots of different programming languages, it's even harder to stay up to speed with what on earth needs to be patched at any given point in time. I actually think polyglot is an option. It's a lifestyle choice. It's not a requirement. There's a cost associated with having lots of different technology stacks involved, and in this area, this is one of them. The flip side is if you're fully automated all this stuff and you're keeping on top of those patch cycles, you're using something like SNCC or a similar service, being polyglot could be a benefit in terms of security. Why? Well, a vulnerability that might affect the JVM isn't going to affect your C service or your Go service. And so again, that idea of defense in depth, having multiple services that have different protections, can be quite beneficial. I'm still not convinced that polyglot makes sense for small teams. Across an organization, absolutely, but I do think the costs sometimes outweigh some of the perceived benefits of using the right tool for the job. It's basically a local versus global optimization problem. We should now talk a bit about response. How many people here have heard about Target? Few people. So Target is a US retailer, big US retailer, and a few years ago they had a rather nasty breach. And basically what happened is basically 40% of all US households were impacted when credit card data was stolen from Target stores. It was a really interesting attack. It wasn't a traditional, oh, let's go and crack your database or find logs lying around. This was actually memory resident malware that was installed en masse on the electronic point-of-sale systems on Target stores across America. And so as you were scanning your card, the malware was actually picking up your credit card details, storing them, and then at a certain date, uploading them. So it's called exfiltration. No, exfoliated. No, that's when you wash your face. Anyway, exfiltrated, that's the word. They were exfiltrated. They sent that data out. It's a really interesting, clever attack, but it got Target big style. The really interesting thing is that Target, unlike most bricks and mortar retailers at that time, did actually have their own in-house dedicated security team. That security team detected the malware being installed. And they said, guys, someone's installing loads of malware on all of our shops. Hello? Is anybody listening to us? And the answer was no. They then spotted the data being sent out of their networks and went, like, seriously, guys? I mean, their data's going. And there was crickets. No one was listening. So this all came out after the fact. I think the CEO lost their job over this eventually. The shares in FireEye, the software that they use to detect this, shot up. The really interesting problem here was they'd done sort of the effort of having a team. The team had detected the problem, but they hadn't properly wired that organization, that part of their security, into their wider organization. They hadn't worked out how to properly alert people. They hadn't properly worked out how to communicate these issues were happening. This was damning indictment of sort of the standard of their security, because ultimately this is almost a classic example of lip service around security. If you want to know more about this and other stories, I can thoroughly recommend Brian Krebs' blog, Krebs on Security. He's an investigative journalist. He spends time on the dark web, so you don't have to. This is good for me because previously I was relying on CSI Cyber for all my information about application security, and apparently that's not entirely accurate, but who knew? A lot of the stuff around response does actually come down to comms and how you handle it. An example of target, this was internal communication being an initial breakdown, followed by some pretty bad things that happened afterwards in terms of how they let their customers know. But comms is all. This is the human factor. This is about having empathy for your customer. How many people have heard of the hacker Ashley Madsen? A few more. So this was partly gained a lot of prominence because of the salacious nature of the site. This is a site where adults could agree to meet up with other adults, and we'll leave it at that. And their website got hacked and all their data was compromised. And the hackers came out and they said, we've got all of your data. If you don't shut the site down, we're going to reveal all of this data. And the people behind Ashley Madison said, you don't have all of our data, you're lying. And they go, we do, and it's been verified by independent researchers. And Ashley Madison said, no, you don't have it. And then they go, okay, you've got a bit of it, but not all of it. And then a few days pass, all right, you've got all of the data, but that's all you've got. You haven't got anything else. And then the hackers say, no, we've got a lot more. We've got all your emails. Okay, and they go, okay, right, so all you've got is all of our data and all of our emails. Oh, and you've also got all of the source code as well. And there was this interesting denial from Ashley Madsen over a period of several weeks. Eventually, they came clean about what had happened, eventually. And this is interesting, right? Because they didn't just front it. You can see lots of good organizations that when these sorts of things happen, get out in front of it. Patreon recently, when they were hacked, did a really good job of saying, here's what we're doing about it. Ashley Madsen were like, oh, no, it's not our problem. We don't know what you're talking about. It's all lies. Another really great counterexample of how to do response well, I think comes from the late 70s, in another story from the US, which is Tylenol. So Tylenol is a pain medication from Johnson & Johnson. It's basically paracetamol. And there was a really sad case in Chicago where I think 6 people were killed when Tylenol was poisoned. Some Tylenol bottles were poisoned. Based on what they think happened, they think it was a local issue. They weren't sure it was certainly wasn't a manufacturing problem. They thought someone locally in the stores was tampering with the bottles. Nonetheless, they weren't sure, but they immediately withdrew Tylenol from the shelves across the whole of the US. The recall, and then they developed mechanisms to protect the bottles. They created tamper-resistant seals and all of those things that are now standard across the industry. That withdrawal process cost them $100 million in 1982 was when this happened. So $100 million because they thought, our customers trust us, right? We can't let them down. We're just going to spend that money and pull it back from the shelves. They never, unfortunately, tracked down how this thing had happened in the first place. The person who did it got away. But nonetheless, when they put Tylenol back on the shelves, a few months later, it went straight back to being the #1 pain medication in the US. It was a huge PR boost. Now, I don't think they were doing this because they thought it was a PR boost. They did this because it was the right thing for their customers. It's about actually having empathy for your customer. And this is often the secret of response and how you deal with things. It's actually putting yourself in the minds of the customer, thinking about what they care about. There was another one of these adult sites that was hacked a couple of years ago in the UK, and one of the senior execs came out and said, don't worry if they didn't get your credit card information. And it's like, what happens if someone steals your credit card? You contact your bank, you get the money put back in, and you have a new credit card in the space of a week, 2 weeks. That's the inconvenience. This site's data that had been hacked, it was all of the conversations you'd had that you thought were private about the things that you like to do with special adult time. right? And that was out there on the public internet. That genie was not going back in the bottle, and yet the exec thought the thing the customer's worried about was their credit card details. The problem often is organizations are responding to these kinds of security issues in the heat of the moment. When people are running around like headless chickens, they're not thinking clearly. The best time to draft a bit of communication to your customers about a data breach is when there is no data breach. Seriously, go back to your offices on Monday and say, what would we say if this thing happened? Let's write the email now while nothing bad's happening. Who's that email going to come from? Oh, is it going to come from our CSO? Is it going to come from the CEO? Maybe the CTO? Okay, right. Well, let's have this. Okay, we've agreed this is what it's going to look like. Great. Now let's save that somewhere. And if anything bad happens, we can pull that email out that was written calmly and sensibly. We update a couple of details and we send it. Don't be writing those things when Twitter is blaring at you, your phone is running off the hook, and everyone's running around screaming, and people are jumping out the windows because you won't think clearly about it all. Let's now talk a little bit about recovery. You've done your best to stop the bad thing from happening. You've detected it. Unfortunately, someone got through. You hopefully then have done the right thing and communicated clearly with your customers about what is needed and how you help them on their journey and what you're going to do next. But you then need to recover your own situation. The easiest thing to do here is to burn the whole thing down and start again. Literally, take a torch to it. A large number of the attacks involve sort of persistent attackers, where they actually install things like rootkits on the machine. They sit there listening to what you're doing and everything else. And you need to burn that stuff out. Of course, that's really easy, isn't it? Because you all have backups, don't you? Hands up if you test your backups regularly. Yeah, about 5 more people that install patches regularly, which is very depressing, but not unfamiliar. Here's the thing, right? With a monolithic system, we sort of have a backup process that's probably mostly manual, and we might test it. With a microservice system, we've got lots more running processes, lots more databases. You have to, therefore, automate your backups, because no one's going to be checking it otherwise. If you've got great backups, are you that worried about a crypto locker attack? No. Just burn it down and recover. But again, most people I know are not automating the backups of their microservice architectures, nor are they actually testing them. My advice would be to find a way to actually use your backup restore process on a daily or at least weekly basis. For example, if you're doing performance tests on a weekly basis, an automated performance test, why not load your performance test data up as a backup from your production environment? That way you're at least testing that on a weekly basis. Build that into your process. If you can do that, you can literally put a torch to everything. You can kill the machines, you can wipe them out, you can rebuild them from scratch. Again, this only works if you've got automated infrastructure set up, if you're actually automating all the things. If you can rebuild your services from source code that's checked in, then you're in a much better place. Now, these are the kinds of things that people do anyway. This automation around building services has got a lot better in recent years. And this is actually a real big aid. Automation isn't just about going fast and developing software quickly. It's also about recovery from security attacks like this. Also, do actually do post-mortems if you can. If you're going to do a post-mortem, actually review how they went, like what happened. Because often, again, we do a post-mortem, and then you publish the post-mortem publicly, maybe. But you never go back and check that you've actually done those sorts of things. But that's a kind of an easy thing to look at. I thoroughly recommend looking up information on things like the blameless post-mortem. John Allspore talks quite a lot about that stuff. But it's a really useful technique for how you get the most information possible out of your post-mortem processes. Okay, so just to wrap up, when you're thinking about application security, I think this 4-part model can help. Think about prevention, stopping bad things from happening. Think about detection. Would you know if a bad thing does happen? Consider what you're going to do around your response when you're thinking calmly and rationally, not when things are going crazy. And ultimately, know how to recover. Work out what your recovery mechanism looks like, and ideally, practice it a lot. Build a constant recovery process actually into how you develop your software. And you'll be much better off if anything bad happens. If there's only one thing you take away from today, it should be to buy my book. If there are two things you take away from today, it's to buy my book and to patch your stuff, okay? Please, if everybody just patched their stuff, a large amount of these problems would go away. So actually go back and have a little think about that. How would we make sure everything is getting patched regularly? I don't think having all your stuff patched once a month is that much to ask. And once you do it once a month, then you can move to doing it once a week. But without further ado, thank you very much for your time. And I'll see some of you later on.
Great. Thanks a lot for your talk.